It shouldn't come as a surprise. I'm not a CISO. Hopefully never will be. This is a rather technical talk. If you're a CISO, you're probably in over your head. Okay, good. It's good if I haven't scared anyone away yet. So what I'm going to talk about today is how to use electronic equipment, apparently. So increasingly, compiler writers are taking advantage of undefined behaviors in C and C++ programming languages to improve optimizations. I've been participating on the C Standards Committee since about 2004. So I actually was involved in the development of C11 from start to end, which has recently occurred to me that now I'm sort of responsible in a way for C. And you know, during that time, we like to think the language is getting better, but more secure. But actually, it's becoming less secure because still the biggest driver for the evolution of C language is opportunity for greater optimization. And the less well-defined the language is, the more opportunity you have to optimize it. You know, so I frequently get into these discussions where we're saying, if 6 turns out to be 9, do you care how fast you got that result? And apparently they do. So frequently these optimizations tend to interfere with the ability of developers or security analysts or security tools to really analyze the code and determine what it's doing, right? And so what happens is there's code that looks like it's there, it looks like it's doing something, but it's actually being removed from the compiler. And then it becomes very difficult for a humans or a source code analysis tool that's not implementation specific to analyze the behavior. So this is leading to increased faults in software, and those are leading to increased vulnerabilities. Oh, there we go, except the wrong direction. So, so some years ago, I authored this vulnerability note with Chad Doherty at CERT. This was April 2008, so this was quite a while ago. And this was about GCC, but maybe in the last 2 weeks, there was the exact same sort of vulnerability was noted in the Clang compiler. So I'm not sure if it took them 9 years to catch up with how bad GCC is, or people just got around to noticing. But some of these open source compilers are sort of the Wild West of compilers, and I'll chat a little bit more about why that's the case. Yep, still going the wrong way. So undefined behaviors. So when I joined the C committee, my goal was to make C a more secure language, and then to change C to make it more secure. And of course, what happened was that C wound up changing me instead. And really, it's a very bright group of people who are involved in the C Standards Committee. And if you give a very bright group of people the set of requirements they were given, they produce the C language. If you give them a different set of requirements, they produce Java. Right, but C is the language that you get given the goals they had, and undefined behaviors. Although this is sort of misunderstood, or they're not there by accident. They're intentionally put there, and the idea is that they're there because they belong there. But one of the mistakes I think the committee made was this term undefined behavior is actually too broad because it encompasses really 3 completely different kinds of things. So the first one is it gives the implementers license not to catch certain kinds of errors that are difficult to diagnose. And so one thing about the committee, C standards written by C developers, C compiler vendors for C compiler vendors. And they don't like to be particularly hard on each other, right? So kind of like, well, hey, Joe, if it's too rough, don't worry about it. Go home, have dinner with your wife, no problem. But this is also meant because there are cases that are MP complete or MP hard that just take too much processing to always know that you're going to diagnose a problem. So consequently, these compilers are not required to diagnose these problems. The second one is to avoid defining obscure corner cases. Okay, so it turns out let's say you have int min, smallest signed integer number, most negative number, and you take the remainder after dividing by -1. Okay, can anyone tell me what result you get? Okay, large negative number divided by -1, what's the remainder? Anybody? If you're thinking this long, you're thinking too hard. 0? You say 0? Yeah, you get 0. Okay, you divide something by -1, there's 0 things left over. It's kind of the same thing as dividing by 1. Okay, on an Intel processor, if you do that, what you get is a segmentation fault. Okay, and in C99, that was what was called implicit undefined behavior. So it was undefined behavior, but they didn't tell you about it. And so for C11, I submitted a proposal, and we discussed it in committee. We wound up modifying the language to make it explicit undefined behavior. And the reason is the C committee doesn't want to publish people who write code for the Intel platform to make them add an extra test to test for this edge condition, because that would slow down their compilers. And the result of that is the burden of doing these checks kind of gets deferred to the programmer. So that's the second reason. The third reason is to identify areas of possible conforming language extension. So here, for example, when you do an fopen on a file, there's a few different modes that you can specify. And if you specify anything else as undefined behavior, okay? So if you put a Y in as a mode, do you think it's going to crash? Absolutely not, right? So the reason they did that was, the standard has to run on a variety of platforms. File systems have a lot of inconsistencies and different features that aren't available on all platforms. So that's a mechanism to allow implementations to extend the behavior of their implementation to match their file system. So that's a third completely different reason. But they're all classified as undefined behavior. And a compiler can ignore undefined behavior completely with unpredictable results. Typically, the committee will say the compiler can go off and play the game of life at that point, and that's allowed for by the standard. The second is behave in a documented manner, characteristic of the environment. So, for example, when you say int min remainder -1 on an Intel platform, it characteristically false. That's the behavior of that platform. That's allowed behavior. Or it could terminate translation or execution with a diagnostic. That's the most you could hope for. So the basic concept, the basic design of an optimizing compiler for C is largely the same as for any other language. Basically, you try to replace computations with more efficient methods that produce the same result. So here's the gross oversimplification I have. Some optimizations eliminate undefined behaviors. We'll call those the good optimizations. And then we have the ones that introduce vulnerabilities, and we'll call those the bad optimizations. By the way, I worked with this. I used to work with David Keaton, who's the chair of the C Standards Committee now, the convener of the International C Standards Committee. And he didn't like the fact that I called this talk dangerous optimizations. He thought I should have just called it optimizations. And that's a little window into the mindset of people in the C committee. Okay, so the C standard specifies the results of a computation as if on an abstract machine, but doesn't specify the methods that are used. So in the abstract machine, the semantics have to closely follow what the specification says, but an actual implementation doesn't have to reproduce all the same steps if it can conduce that, for example, value is not needed, or that there's no side effects occurring that would require, that code to be executed. So basically, the compiler's optimizer is free to choose any method that produces the correct result. So this gives the compiler the leeway to remove cause that's deemed unused or unneeded when building a program. And this is typically referred to as the as-if rule, because the program has to run as if it were executing on the abstract machine, but it doesn't have to follow all the exact methods. And occasionally, you'll see a little bit of, you'll see two places in the standard. You'll see a volatile with volatile and with memset underbar s, where there's language in the standard that says must operate, according to the rules of the abstract machine. So those are two places where the standard says that, you can't, the as-if rule doesn't apply. You have to implement the semantics exactly. So volatile, for example, if you say x equals x, and x is volatile qualified, you need to read the variable x, and then you need to write the variable x back out. But if that wasn't volatile qualified, that code would be optimized out for sure. Okay, so compiler vendors use various implementation strategies. One strategy is hardware behavior, where you basically generate the assembly code and you let the hardware do whatever the hardware does. And for many years, that was kind of how C worked. So, the people in the room with the gray hair, the white hair, or the no hair probably have been exposed to that type of programming. Another model is super debug, where you trap any undefined behavior. Great for debugging, very impractical for deploying code because it has significant slowdowns. And third is total license. In total license, you can treat any possible undefined behaviors as a can't happen condition, which allows you to optimize aggressively. So just to start with a simple one, constant folding is the process of simplifying constant expressions at compile time. So constant expressions can be simple literals, such as the integer 2. Variables are never modified, or variables that are explicitly marked as constant. So again, to go back to my old example, if you get your Intel processor out and you say int min remainder -1, you print the result that says 0. And that gives you a sort of a misleading sense of warmth that your implementation is going to produce a 0 result. But what's happening in this case is that int min remainder 1 is a constant expression. So it's actually the compiler that replaces that with a 0. So there's no runtime code being generated. So if you were to replace this code, and I think I have. So here's this code compiled on Microsoft Visual Studio with optimization disabled. So, these optimizations are so automatic that you cannot disable them. They just happen. And you can see that we're just pushing 0 onto the stack and printing it out. So there's no division operation being generated here. So if you actually want to see what's happening, you have to use sort of non-deterministic values. And then you can see that we're going to generate an IDiv instruction, which will now fault when you provide int min and -1 as the arguments. So a little lesson here is that when you're writing these little tests to test behavior, be very careful that the program's doing something. Otherwise, the compiler is very, very likely to optimize out your little test, and you're not going to be testing what you think you were testing. Okay, so this is the kind of the major vol that I'm going to chat about. This is the one that Chad and I published back in 2008. But the thing is, it's not really a vol. This is how the compiler works, and it still works this way today. So when you read the C standard, there's a clause that says when an expression that has integer type is added to or subtracted from a pointer, the result has the type of the pointer operand. So that's basically just defining pointer arithmetic. And array indexing notation is sort of a syntactic veneer for pointer arithmetic. If you index an array P at index n, it's just going to expand to P plus n scaled for the size of the element type and then dereferenced. So C goes further to say, I got a laser pointy thing on here. I can remember. Oh, here we are. So what this paragraph says is that you can form this pointer and dereference this value, and you can form every pointer up to here, and you can dereference this value. And the C standard requires that you can form this pointer. Okay, this is well-defined behavior. The C standard has to support the formation of this pointer, but if you dereference this value, it's undefined behavior. And if you form this next pointer, it's also undefined behavior. So what the C standard allows is that you can form the one too far pointer, the too far pointer. And the reason for that was in the early days of C programming, people wrote loops where they incremented the pointer and then tested to see if it was this one and then stopped the loop. And so the standards committee decided to allow that behavior. And so it's now enshrined in the language. Okay, so a typical thing a C programmer might do if they've taken my secure coding in C and C++ course is they might decide we should be concerned about buffer overflows because they've got unintended consequences. To do that, you might have say a pointer to the beginning of an array, a pointer to the end of the array, and you might have a size, which you would express as a size t argument, not an int. And part of my secure coding course, I have 1 day committed to talking about integers. So if you ever have time for that, I'll explain why it needs to be size t. But the easy thing is just to declare it size t for now. And so we'll do a test to see if pointer plus len is greater than max. That means we're trying to reference a location beyond the bounds of the array. And so we'll return an error condition in that case. But no matter what your implementation is, what your model is, there's a bug in this code, which is for very large values of len, pointer plus len can wrap around, which would create undefined behavior. And under the hardware behavior model, the result would typically wrap around and point to an address that's actually lower in memory than pointer. Okay, so to fix the bug, an experienced programmer who sort of internalized this hardware behavior model of undefined behavior might add a test where they test to see if pointer plus len is less than pointer to detect the wraparound behavior. Okay, so the reason I said experienced programmer there, and I'll give you a little more insight into the C standards committee. Okay, say you're trying to get a feature or something changed in the C standard. The best way to do that is say, hey, I work for Intel, and we've just added this vectorized instruction, but there's no way to use it from C code. Can we modify the C language so that programmers can use our new vectorized instruction? And they'll say yes, because the C standard they like to support hardware. That's the purpose, is to give you access to the hardware. Okay, the second thing you could do is you can go and say, we've noticed that naive programmers frequently make the following error, right? And it turns out the C standard committee does not give a shit about naive programmers, okay? So that argument doesn't fly at all, We had an hour discussion about some behavior where no one in the committee knew the answer. We had to spend an hour kind of going back and forth till we could sort out how something worked. And then a guy from Cisco, who doesn't have a compiler, he's just got a bunch of developers, said, and you expect developers to know this? And in unison, the entire committee said, yes, absolutely. So if you come to them and you say, an experienced programmer such as yourself might make this mistake, you've got a chance of them listening to you. So that's why it was couched in these terms. So a compiler that follows a total license model, like GCC and now Clang, may optimize out the first part of this check, leaving the bounds defeated. Okay, so the reason for this is because if a pointer plus an unsigned len compares less than pointer, then undefined behavior has occurred. Okay, so the exact undefined behavior that has occurred is that if I take a pointer to this array and I add a size, and now I'm checking to see if it wrapped around, without a doubt, I just try to form a pointer which was outside the bounds of the array. And by this language in the standard, that makes that undefined behavior. Okay, so this code invokes undefined behavior. So consequently, the compiler can assume undefined behavior doesn't occur, and it can remove that code as dead code. Okay, so that sounds bad, but then when you look at it, you start to see how this comes about, right? So what's going on here? The optimization is called algebraic simplification, which sounds like something we all did in 6th grade algebra. So the optimization says that optimization may be performed for comparisons between P and V1 and P and V2, where P is the same pointer and V1 and V2 are integer variables. And so total license model allows that to be reduced to a comparison between V1 and V2. However, if V1 or V2 overflow when added to P, the results of comparing those two values directly is not the same as doing the arithmetic and then doing the comparison. And so one of the fun things about digital arithmetic is that because of possible overflows, computer arithmetic doesn't always obey the algebraic identities of mathematics. So it does. There are mathematical models that describe digital arithmetic, but they're not the ones you learned in 6th grade. Okay, so if you go back to our example, what you'll see is this expression pointer plus less than pointer is the same. We can add 0 to the right-hand expression without changing that. Now basically we have a comparison of P plus V1 compared to P plus V2. This can be simplified to a comparison between V1 and V2, and len cannot be less than 0 because len is unsigned. So consequently, this code doesn't do anything, and the compiler removes it. Okay, and consequently our bounds check has been defeated. Okay, so once you're aware of this problem, it's actually quite simple to fix. So if you know that pointer is less than or equal to max, which we do in this case because pointer points to the beginning of the array and max points to the end, you can just subtract pointer from both sides and compare to see if len is greater than max minus pointer. So this won't wrap around because max is greater than pointer, and consequently there's no undefined behavior here, and the compiler is required to evaluate this expression at runtime to generate the code and evaluate the expression. So this code will always succeed, and it's a very easy fix to make, but developers aren't always aware of this. And in fact, this particular defect occurred in the Plan 9 code written at Bell Labs. So when I say experienced programmers make this mistake, those guys are pretty experienced. Okay, so thanks to the magic of Google and the internet, you can Google the history of this on like the GCC dev list, and you'll see that a lot of people said a lot of bad things to me when I tried to report this problem on the GCC dev list. So one thing that developers came back with was they said, well, hey, if you have something like this, this actually works to your advantage because it'll simplify this to a comparison between n and 100, and that eliminates possible wraparound in both those expressions. So this would, the optimization here would eliminate undefined behaviors. That makes it a good optimization. In this case, it's probably not a big deal unless one expression wraps but not the other. So, but you don't want to ship this code, and the reason you don't want to ship this code is because optimizations are optional, right? They're not required. You don't want to depend on an optimization to make your code correct. And so as a developer, what you'd want to do is perform the simplification yourself and ship this code and not rely on the compiler to make your code correct. Now, the other thing I'll say is, a lot of developers would spot this code, but frequently the problem is that this sort of thing is hidden in macros. So it's not apparent when you look at the source code. It's not apparent this is happening until you see the macro expansion. No questions so far? I scared a couple people away. They're like, wait a second, I'm a CISO, and this guy is speaking some odd language. I don't understand. Okay. So the behavior pointer overflow changed as of the following versions of the compiler. I believe we're now on GCC 7.1, so this has happened a while ago. But one of the things you'll see here is that this changed in a maintenance release. Okay, and when you look at portability behaviors, undefined implementation defined, unspecified behavior, and undefined behaviors are all portability issues. But undefined behavior is the most severe, right? Because there is no specification of that behavior, and so the compiler can do whatever it wants, right? And I say a lot of things that sound like compiler writers are evil, but they're trying to do the best they can for your code base, right? So usually what they're doing is when they see undefined behavior, they take a guess as to what maybe you were after, right? But if they guess wrong, if their guess doesn't meet your expectation, then you're going to have a defect. And the other thing that happens with undefined behaviors is that compiler writers look at these as opportunities for optimizations. And so when when they're done writing optimization, they'll release it as part of a maintenance release. And if your code had undefined behaviors, it may have worked previously, and now it might fail because the compiler now deals with that undefined behavior differently. So this particular optimization is performed by default at O2 and above, include optimizing for space, not performed at O1 or O0. It can be enabled with the strict overflow option or disabled for O2 and above with the no strict overflow option. The only way you could, okay, so here's how this optimization came about. There's a guy named Ian Lance Taylor, and he's at Google, and he implemented this optimization, okay? And of all the people on the GCC dev list, he was the only one who didn't, scream at me. He was the only one who had like a rational conversation with me. And basically, okay, here's Google's kind of deal, right? They have a few applications they run a lot, okay? So they have these farms of computers, and they looked at, they looked at this optimization, and they discovered, well, we could get a 0.5% improvement. That would allow us to get rid, and we know our code doesn't have this error, right? And it would give us a 0.5% improvement. We could get rid of this number of machines and save $400,000 a year, right? So it looks really good to them to do this optimization, so they do it. And then everyone else gets this, and your code base maybe does have this problem, right? So, so we had discussion with Ian, and basically they kept this optimization in, right? But what we agreed was that they set a flag to notify you that the optimization was being performed. So what you can do now is you can set strict overflow equals n, where n is greater than or equal to 3, and now the compiler will warn when this optimization is taking place. Now the problem is this is not included in WAL, okay? And probably the only way you would find out about this is if you came to my talk. And if you came to my talk, you'd probably know not to have this undefined behavior. So today this is still, a pretty significant problem. Okay, so there's a bunch of GCC options. F strict overflow allows the compiler to assume strict signed overflow behavior. Signed arithmetic overflow is undefined behavior, so the compiler will assume that it doesn't happen, and that permits aggressive optimization. So for example, if you write I plus 10 greater than I, the compiler would just assume that's always true for any signed value I. And of course, that's only true if that expression doesn't wrap around. So when this option's in effect, any attempt to determine, okay, so this is kind of a key to this. So the worst code is code that's written for security, either by developers or by security folks, okay? And part of the reason is it's very easy to invoke undefined behavior when you're testing for undefined behavior, right? So you kind of say, hey, does this undefined behavior exist? And the compiler says, oh, he's just invoked undefined behavior, and they take your test away. So your test disappears. So when you're writing tests for undefined behavior for security vulnerabilities, you have to be very careful not to invoke undefined behavior. So FRAP-V instructs GCC to assume that signed arithmetic overflow of addition, subtraction, multiplication will wrap around. So it's similar to no strict overflow, and it will disable optimizations that assume integer overflow behavior is undefined. So this is the option that was enabled for the Java front end as required by the Java language specification. So the Java language only has signed integers, and the signed integers have well-defined wraparound behavior. In C, you have unsigned integers, which have well-defined wraparound behavior, and you have signed integers, which have undefined behavior on overflow. And of course, now GCC doesn't have a Java front end anymore. It just got removed as of 7.1. Okay, so strict overflow equals n. This, of course, only applies when strict overflow is active, right? So in other words, this flag to diagnose this problem, this optimization, is only going to be triggered when you're performing the optimization. So if you, so you have to make sure that you're optimizing your code in order to detect these optimization errors. So there's 3 warning levels. So in optimization, which assumes signed overflow doesn't occur, so this is always kind of the problem with C, right? So one of the premises of the C language is trust the programmer, right? And a good example of that is, say you take an int and you assign it to a short, right? The compiler will look at that and think, that looks pretty dodgy, right? I mean, clearly you can't store all the values that can be represented as an int in a short, but we're going to trust the programmer, and we're going to trust that the programmer knows that the range of values being stored in this integer can be represented as a short. We're going to go ahead and make that conversion. And the same thing is true with these, this code, right? These expressions don't necessarily overflow. It depends on the values that they take. So at a setting of 1, it will warn about cases that are both questionable and easy to avoid, such as x plus 1 greater than x. With strict overflow, the compiler will simplify this to 1. And this is the only level that's enabled by wall. Higher levels aren't and have to be explicitly requested. So strict overflow equals 2 will tell you about other cases where comparison is simplified to a constant. So for example, if you take the absolute value of a signed integer value, it will return a negative value for the most negative. So if you say absolute value of int min, the answer is int min. You get the same negative value back. And that's because on a 2's complement machine, you can't represent the negation of int min. So level 3 is we'll also warn about other cases where comparison is simplified. For example, x plus 1 greater than y being simplified to x greater than 0. And this is the lowest warning level, which will warn on the specific optimization I was describing earlier that eliminates the bounds check. Strict overflow equals 4 will also warn on other simplifications like this arithmetic simplification, which I would think in almost all cases you would want to have this. And then 5, will warn about cases where the compiler reduces the magnitude. So we've some of the work I've done in the C Standards Committee, we introduced a C analyzability annex into the C11 standard. It's a normative but optional annex. So not everyone has to implement it. I know for certain the Oracle, the old Sun C compiler guys, they're implementing this annex. So what we did was we added a couple definitions. So we defined out-of-bounds store, and we defined bounded undefined behavior as undefined behavior that doesn't perform an out-of-bounds store. And then we defined the term critical undefined behavior, which is basically the old style of critical undefined behavior. So there are, by the way, 200 explicit undefined behaviors in the C language. And all 200 of them used to be critical undefined behaviors. So the requirement is that basically, besides a short list of critical undefined behaviors, all undefined behaviors have to be bounded undefined behaviors if your compiler implements Annex L. And so now, instead of there being 200 undefined behaviors you have to worry about writing out of bounds, you're limited to 9. And the 9 are this particular list, the sorts of things that usually result in that. Okay, so to kind of wrap this up, and the wrap up here, sometimes my recommendation surprises people at the end of this, which is, ignore undefined behaviors. That's not a surprise. Having undefined behavior in your code doesn't mean your code is wrong, but it means that the compiler can change, and a future version of your code might be wrong. And so it's best not to depend on undefined behaviors. I would recommend trying to find and eliminate dead code instead of letting the compiler do it. So if you can use a strict overflow flag to indicate it's rewriting the code because there's undefined behavior, like that example of, n plus 100 compared to, n plus 3 or whatever, do the simplification yourself so you're not relying on the compiler to do the optimization. So we've seen that some optimizations can eliminate undefined behaviors while others will introduce vulnerabilities. So a lot of security people who don't quite know what they're talking about will, well, first, a lot of people will ignore this completely, right? Not know anything about this, but then you learn a little bit about it, and then you think, oh, we should enforce wraparound behavior. And frankly, that's not the recommendation I would give. And the reason is because you're turning off all the optimizations, and many of those optimizations are fixing your code, and some of those optimizations are breaking your code. But generally speaking, if you just turn them off, your code is going to get worse in terms of quality and security, and it's going to get slower at the same time. So my recommendation is go ahead and build optimized code, but turn on the warning flag to find out where the compiler is doing these optimizations for you, and take a look, and if it's optimizing on an assumption that's different than your assumption's wrong. And you need to revise your code. Finally, tell your vendor to implement Annex L and use it because it's cool. And finally, the C standard is a contract between compiler writers and programmers, but really only compiler writers show up for these, and me, and the guy from Cisco. And so we've had votes that have been 30-2, where Cisco and me vote the same way and everyone else is against us. And sometimes the reason is because, well, that's hard to do, so they don't want to do it. So the contract's continually being amended. And unless more security conscious groups sort of get involved, the tendency is to eliminate guarantees from the standard. It's kind of like getting divorced from your spouse and telling your spouse to just handle the divorce and you'll be happy whatever the outcome is. That's not going to work out good for you, my friend. Okay, so I'm done. I'll take some questions. Yeah, sir. Yeah. Yeah, I teach at conferences. I did a 3-day course here on secure coding in Java, but we also come on site and deliver on site. And the on-site deliveries are generally more popular just because it's easier to fly me somewhere than it is to fly 30 people to a conference. But yeah, let me know and we can come to your site and deliver that for you. Sir? How do compilers tend to be? Oh, other compilers? I haven't looked at all of them. I now know that Clang behaves similarly. Visual Studio, for however much people hate Microsoft, I mean, they're a little bit more reasonable because they're controlled by one vendor. They don't have this Wild West where everyone's looking out for their own interests sort of thing. So it's kind of, you have to look, I mean, I'll tell you some other like random frightening things, but when you get a C compiler, it will have there'll be an implementation, a set of flags where it conforms to the standard. It might not be the default set of flags. So, the out-of-the-box compiler you use might be non-conforming to the C standard, So some of those compilers do really wacky things. The IBM compiler actually treats unsigned integers as wraparound as undefined behavior, which is a violation of the standard. So by default, it behaves in a non-conforming mode. But they basically, these compilers grow up with their users and their code bases, and they're sort of designed to work with the code that's, uses these compilers for compilation. Any other questions, sir?
Static analysis tools pick up this dead code very often.
This is a problem generally for static analysis tools because a lot of static analysis tools work for multiple different platforms, right? So they can sell it more widely. And so it's kind of very difficult for them to know what the specific optimizations are that different compilers are performing. So this class of problems frequently not diagnosed. And that was actually my first slide, that these optimizations really make it hard for human analysts, static analysis, or anything else to detect. And certainly, the thing that irritates me the most about all of this is, when the compiler vendor says, hey, this is undefined, I can optimize here, they know it's undefined. They could generate a warning at that point, but usually they don't. So you have to kind of bug them, to, like this GCC case, to go back and add the warning. So anyone's even being notified that the undefined behavior is there. I mean, they know it's there, and they're frequently not diagnosing it.
A lot of developers don't even look at warnings, though.
Sorry?
Many developers don't look at warnings.
Oh, yeah. So you should look at your warnings. I mean, so I've had a lot of customers who are going to go buy Fortify or Coverity or some expensive analysis tool, but they aren't, they don't have their warning levels set and aren't paying attention to the warnings. I have done a study while I was at CMU, and really the compilers are more effective at diagnosing these type of problems than the analysis tools. So before you go, I think, you should use static analysis tools, but before you buy them, set your warning level to the highest level and address those warnings. And, address them smartly, because a lot of people will go in and say, well, if I put cast all over the place, it'll shut the warnings up. Okay, now your code's worse than it was before, because you have all the same problems, but now you're not getting diagnostics anymore. Okay, any other questions? This is fun, come on. Let's keep going. No? Yeah.
But new developers, you were saying in the beginning that the C language has actually become more insecure.
Yeah.
Are there now maybe new developments in the standards committee that add new, more secure features to the C language?
It's a little bit of give and take. I mean, so there are places where guarantees are weakened. I'll give you a quick example. When you read on initialized memory now, this committee's introduced a concept of wobbly values, right? So that means that every time you read an uninitialized value, you can get a different value. So you could have an expression, you could say if X, do this, and it would do it, and then down below you can say if not X, do this, and it would do that too. Because if it's uninitialized, it can now vary every time you read it. So that's an area where the language is becoming less defined. But we've added Annex K, which is balance checked interfaces. Those are nice secure functions. We've added memset underbar S, which can't be optimized out, so it lets you say clear passwords from memory before you pass that memory to free. Normally, if you just say memset and then free, that memset is always optimized out because it's a dead code store, and developers don't realize that. Whenever you see memset followed by free, it's basically a vulnerability because they're trying to clear it out, but it's not going to happen. So yeah, it's back and forth, but basically you need to just, you just need to know how the language works and program correctly. Well, yeah. I mean, there's no substitute for knowledge. Okay, anyone else? I'm having fun, so yeah, sir.
Maybe an easy one. You mentioned that the -02 and -03 basically set the warning level to 1 with a strict optimization. Is it actually auto-dependent which value the compiler actually uses, or is it basically when you set it to 3 or 4 that it always wins?
Oh, well, I think what I was trying to say with those slides is that if you want to test for the existence of these optimizations, you need to do two things. One is you need to have the strict overflow flag set, and you also need to have the optimizations being performed. So you have to set strict overflow on, or set a high optimization level, so it's going to optimize the code in order to get the diagnostics. So if you just set strict overflow and you hit optimization 0, the order doesn't matter, but you need to specify both. If it's not optimizing, it won't diagnose the optimizations. Okay, any other questions? You were recording all this, right? That's good. Now I'm running back in my head, like, who'd I insult? Google, IBM. Any other questions? Okay, thanks that ends the CISO track, I think, for the week. Okay, thank you very much.